Swayam Prabha. Digital India. Educated India.
Okay. So, why is it that I should consider in this particular unit? What advantage do I get? No. See, please note that we are using a logarithmic scale, right? So, if I have log omega and log of 10 omega, what is log of 10 omega? What will I get if I go one decade essentially above or below omega? 1 plus omega, 1 plus log of omega. So, what do I get out of it? We will see. Okay. So, when we plot the Bode diagram, we will figure out what are we going to essentially get out of it, right. So, please wait for maybe some more time, maybe next class we will be able to figure out why it is done. Okay. There is another region which is band which is used, which is called as an octave. Okay. What is an octave? Let us say you give a frequency omega, the region what to say omega to 2 omega is what is called as the region 1 octave above omega. Similarly, from 0.5 omega to omega is what is called as 1 octave below omega. Okay, so these are all some terms which are typically used. Okay, that's a decade and an octave. Okay, so please remember that, and you will see that like by and large like we express slopes in these curves in terms of decades or octaves. Okay, like so because we want to typically see how the magnitude curve or the phase curve it changes as you vary frequency from by a factor of 10 or 2. Okay, so that is the convention, and that's what we will see, okay, as we go later on, right. So, why we are essentially varying it by 10 times. Okay. So, that is the first factor like where we consider g of s to be just a constant, right. Okay. So, please remember this octave and decade and so on, right. So, now let us plot the Bode diagram for 1 by s, right. So, what is going to be the Bode diagram for 1 by s? So, g of j omega is going to be 1 by j omega, right. So, this implies that the magnitude of g of j omega is going to be, we discussed this yesterday, right. So, if you have a complex function, it is a ratio of individual factors, the magnitude is going to be just the ratio of the individual magnitudes. So, here it is going to be 1 divided by what is the magnitude of j omega? Omega, that is it. Okay. So, this implies that 20 log to the base 10 magnitude of g of j omega in decibels is going to be what? 20 log to the base 10 1 by omega. What is log of 1 by omega to the base 10? It is minus log omega, right. So, we are essentially going to get minus 20 log to the base 10 omega. Of course, omega is positive, right. So, it is frequency, it is a positive number. So, I am not putting a absolute value here, right. So, I hope it is clear how we got this, right. So, because 20 log to the base 10 of 1 by omega is going to be minus 20 log of omega, right. So, that is what we have in decibels measure, right. Okay. So, that is the magnitude. What about the phase? Phase is once again going to be the algebraic sum of the numerator and the denominator factors. Numerator is 1, the phase is 0 degrees, denominator is j omega, the phase is going to be 90 degrees. So, the phase of 1 by j omega is going to be minus 90 degrees, right. Do you agree? Okay, because if you go to the complex plane, okay, 1 is going to be here, right? So the vector 1 is going to make an angle of 0 degrees with the positive axis. Where is j omega? J omega is somewhere here. So this face is going to be 90 degrees, right? Correct? So totally the net face is going to be 0 minus 90. So we are going to get it as minus 90 degrees. That's the phase contribution of 1 by j omega. So immediately you see that, like this is independent of omega, right? It's constant with respect to omega, whereas the magnitude is a function of omega, right? So that's minus 20 log to the base 10 omega, okay, in decibels. Now the question is that how do I plot them, right? So let's plot them and then see how we get those values, okay. So let's say, I start with 1, I go 10, then I go to 0.1, and this is the magnitude of g of j omega in decibels, right. Similarly, we have the phase diagram. Phase diagram is pretty easy to plot here. So the phase of g of j omega in degrees, okay. So once again, let's say I have 0.1, 10, 1, 0.1 and 10, right. So the phase diagram is pretty easy. So there is going to be a straight line, a horizontal line at minus 90, right. So that's what I have, right, for the phase, okay, for this particular factor. But what can I say about how can I plot the magnitude plot? So that's going to be minus 20 log omega, right. So essentially when omega is equal to 1, what is the value? Let's say you substitute omega equals 1 radians per second, right, in this magnitude value, right. What do you get? What is log of 1 to the base 10? 0, right. So you get as, let's say this is my 0 decibel value, okay. So let's say you substitute omega equals 10, what do we get as decibel measure? We get minus 20, right. So at, let's say omega equals 10, I get the value as minus 20, and let's say I substitute omega equals 0.1, what do I get? Plus 20, right. So at omega equals 0.1, I get plus 20. So immediately you see that the magnitude curve is going to be a straight line because it is a non-linear function of omega, but then you can see that it's a linear function of log of omega, right. See, if you call log of omega to the base 10 as x, this is like minus 20x, right. So it's a straight line once you have the abscissa in the logarithmic scale, okay. So that's why we get a straight line, right. And you can immediately see that the slope of this line is negative, right. So because as omega increases, the value is decreasing, right. Now what do you think should be the slope of this line? The slope of this line is the way we calculate it is the following, right. Because the function under consideration is minus 20 log omega. Let's say at 10 omega, what are we going to get? We are going to get minus 20 log to the base 10 omega decibels. So this is going to be minus 20 and minus 20 log to the base 10 omega, right. So you take any omega, okay, the value is going to be minus 20 log omega decibels, right. You go to 10 omega, what's going to happen? The value is going to decrease by 20 decibels, right. That's what we can have, right. At any omega, the magnitude is going to be minus 20 log to the base 10 omega. You go 10 omega from that omega, the value is going to decrease by minus 20 decibels. So for that reason, the slope is indicated as minus 20 decibels per decade, okay. So in one decade of frequency, the magnitude essentially drops by 20 decibels. Okay, that is the slope of this magnitude curve. Okay, I hope it's clear how we got this slope. And one can also illustrate this in octave. Let's say at 2 omega, what's going to be the value of this magnitude? It's going to be minus 20 log to the base 10, 2 omega decibels. So that's going to be, what is log of 2? To the base of 2, I think it's 0.3010, right? So you multiply it by minus 20, you are going to get approximately minus 6. Am I correct? So this is going to be approximately minus 6 minus 20 log to the base 10 omega decibels, right? So consequently, people will also say that the slope is minus 6 decibels per octave, right? That means that in 1 octave from a frequency omega, the magnitude will drop by minus 6. Okay, so that is the other way people will write the slope. Okay, I hope it's clear how we calculated the slope, right? This is a straight line, so we are just calculating in this manner. Okay, is it clear? Right. Okay, so that's what we have. Okay, as the Bode diagram for the factor 1 by s, right? So that's the in general what we call as an integral term, right? 1 by s is an integral term. So now if I want to consider g of s to be s, what do you think will happen? Let us say g of s, I take it to be s. Okay, let's repeat the same things. So it's pretty straightforward. Okay, once we know the process, this is going to be g of j omega is going to be j omega. So this implies that the magnitude of g of j omega is going to be just omega, right? So this implies that 20 log to the base 10 magnitude of g of j omega in decibels is going to be equal to 20 log to the base 10 omega in decibels. So previously we had minus 20 log to the base 10 omega, now we are having plus 20 log to the base 10 omega, right? Okay. So what about the phase of g of j omega? It is going to be 90 degrees. Okay, so that's what we are going to have, right? So the phase is going to be 90 degrees, right? So that's what we will have, correct? Yeah, because j omega is on the positive, what to say, imaginary axis. The phase is going to be 920 degrees. Sorry, 90 degrees, right? So that's what we are going to have. So now you can immediately plot the magnitude plot on the phase plot. I am just going to draw on the same diagram. Okay, you kindly draw it in a different diagram. Okay, see, because I am drawing it on the same diagram to just show you a point, right? So let me let's first draw the phase. Okay, the phase is going to be plus 90. Okay, so this is for the factor g of s is equal to s. Okay, this was for the factor g of s is equal to 1 by s, right? So let me write down this. This is for g of s equals 1 by s. Now how will the magnitude plot look like for s? So that's 20 log omega, right? At omega equals 0, once again we are going to have 20 log 1 to be 0. At omega equals 10, what are we going to have? It's going to be plus 20 decibels. Oops. Okay, so at omega equals 0.1, we will immediately see that it's going to be minus 20 decibels, correct? So now if I join this, this is going to be in this way. Okay, so this is the magnitude plot for the factor s. So what do you think is the slope of this curve? Once again a straight line. It's going to be plus 20 decibels per decade or 6 decibels per octave, right? That's going to be the slope of this curve. Okay, so that's the difference, right? So can you observe something from here? I hope it's clear how I plotted it, right? Pretty straightforward once we get a hang of what is happening, right? So how did we plot this? Using this the formula, right? And what can you observe from these plots? Any observations? See, please note that 1 by S and S are reciprocals of one another. So what can you infer from this plot? In a certain sense, it's going to be a mirror image, right? Correct? The phase plot and the magnitude plot. But mirror image about what axis or what point? Omega equals 1? Y equals 0? Sorry, what is it? At point, what is say 1 comma 0? Is it? Okay. So we will please what to say, keep this question in mind. Okay, when we go to the first order factor with a constant term and second order factors, I will ask you this question once again. Then you will be able to generalize, okay, and give a general answer. Okay, what happens to the Bode diagram when you have two factors which are reciprocals of one another? See, at the end of the day, think about it. Okay, if you have let's say a reciprocal and the factor itself in a transfer function, what will happen? They will cancel off each other, right? So what should be the net magnitude and phase? It should be 0. That's what is happening, right? You add, right? Because we are going to logarithmic scale, you add the magnitude at any frequency, do you get 0? Obviously you would. Similarly, you add the phase, you will get the answer as 0, right? So that should give you the hint, right, as to what should be the line about which it should be a mirror image, right? That is the horizontal line passing through 0, right? So about that, it will be a mirror image, right? Because obviously you want the sum to be 0, right? Because there are reciprocal factors of one another. Okay. So so what I am going to do is that, like, I am going to essentially so what we have done till now is that we have done 3 factors, right? So we have done K, we have done 1 by S, we have done S, right? So what we will do is that, like, we'll do the first order factor in the next class, okay? But before that, of course, once again, like, just so that you remember, so what do you observe it? Observe about factors that are reciprocals of each other. Okay, so that's a question which we just answered, right? So I am just phrasing the question so that you remember, right, that we discussed this, right? So just to basically convince ourselves that, like, given any particular transfer function, we would be able to rewrite in this manner. Okay, just to essentially look at that. Let's say we consider some function like some arbitrary function s plus 2, let's say s cube plus let's say 4s squared plus 3, something 3s. Okay, so something like this, right? So what can I have? What can I do? Like, if I have a Planck transfer function like this, I can rewrite this as s squared plus 4s plus 3. And what is s squared plus 4s plus 3? It is going to be s plus 1 times s plus 3, correct? So this I can rewrite this as 2 times s by 2 plus 1, correct? And 3 times s times s plus 1 times s by 3 plus 1. Okay. So, this I can plant transfer function I can write as 2 by 3, correct, times s by 2 plus 1, I am rewriting in this way, times 1 by s times 1 by s plus 1 times 1 divided by s by 3 plus 1. Is it clear how we broke it down into the factors that we have learnt or we are going to learn, right? I hope it's clear, right? So, even you can have a s by a term, you divide by a, right, pull a out of the term, right, so that you make the constant one, and then you factorize all the constants, anyway you will get some constant outside, that is okay, right. So, you can see that we have learned how to plot the Bode diagram for the constant and the 1 by s term. What we are going to do in the next class is that we will learn how to plot the Bode diagram for 1 by ts plus 1 and ts plus 1 and then the second order factor. Okay, so that is what we are going to do. Then we will see how to put everything together and plot the Bode diagram for any given transfer function. Okay, so that is what we will do in the next class. Fine? Okay, any questions? Okay, so if not, I will just stop here and then we would meet and then continue next class. Okay, thank you.